Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchats, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first 3: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested of course and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Okay. So let's start then with the vectors. Imagine, for example, that I have a vector here. Can you see? Yeah. So this vector here, I'm going to say this is vector A. Okay? And what distinguishes this from a scalar, for example, I can write here something like this. Scalar vector. Okay? So, scalar, we only have the intensity or the value, right? Value, intensity is a bit... Okay, let me see if I can write better, sorry. For example, if you have a velocity vector, or the scalar of the velocity is going to be its value or the speed, right? Vector, you have more, so you have also intensity, but you also have one very important thing, which is direction. So with vectors, you also have information regarding direction, right? So, for example, if you have here point A and point B, this vector A will tell you how to go from point A to point B in a straight line, right? So that information is included in a vector, but is not included in a scalar. The scalar will only tell you the norm or the intensity of this vector, right? It doesn't include any information regarding the direction. So this is basically the most important thing that distinguishes a vector from a scalar. And this introduces an additional problem, which is, okay, the vector gives us the direction, so we need to understand or describe that direction in a coordinate system. Okay? Right? So that's another thing we have to do with vectors. We have basically to for example, if I have here vector A again, I will have to say this vector A will have to have a coordinate system that I will say X, Y, right? I'm doing in 2 dimensions. I'm doing a 2-dimensional analysis. So this coordinate system here is going to be my referential, if you want, that will allow me to obtain the direction of vector A. And how do I do that? Well, I have to decompose the vector A in X and Y directions. So the way you do that is you draw parallel lines to the axis, okay? And then you say, this is my component in the X direction. I will call it AX is still a vector, right? And this is going to be the component of my vector in the vertical direction. I will call it AY. All right? So it's quite easy to understand this. You have a vector A in red. You need to have a coordinate system to describe this vector. And then what you just do is you just draw parallel lines to this coordinate axis. And the intersection of these lines with the coordinate axis will give you the location of the components of this vector AX and AY. Right? Okay, so one more thing we need to understand is that this coordinate axes, x and y, in order to define, they are also vectors, right? This x and y, they are also vectors. So in order to define the direction of these vectors, we usually use a unit vector. We call sometimes versors. Okay? So if I do that, so I'm going to do that in black now. So I'm going to say that this unit vector I'm drawing here, I'm going to zoom in a little bit. I'm going to call this my I unit vector. So unit vector means the norm, the norm of this I vector is equal to 1. The norm or the intensity or the value of this vector is equal to 1. So it's a unit vector. So what is the information that we get from this unit vector? The information we get is the direction only, because its norm is equal to 1. And that direction is the direction of my x-axis, right? Same thing for my y-axis. I can also have here a unit vector in the y direction that I will call it j. Again, the norm of j is equal to 1. Is a unit vector as well. The only objective of this vector is to give me the direction of my y-axis. And then I can say something like this. I can now say that my vector A will have a component in the x direction, which is going to be ax. So this ax I wrote here in blue is basically what? Is the norm, or the, if you want, is the length of this ax vector here, is the length or the intensity of this ax vector. So this gives me only the intensity, but I need to have also the direction of this ax. How do I get the direction? Well, the direction is given by this unit vector I. So I need to multiply now this by my I unit vector. So if you look carefully, this product here will have information. So this is going to be my ax vector. A vector now, right? This ax vector is the same as this here. I will have information about the intensity of the vector, is this ax scalar. And I have information about the direction of the vector, which is this I unit vector, right? But this is not completed yet, because I need now to add, in order to obtain my vector A, in red, in the figure, I need to add now the y component of the vector. So I'm going to do in a similar way. So this y component is going to be ay, and I need now to multiply this by the unit vector along the y direction, which is my unit vector j. Right? So this product here, this is going to give me my ay vector. All right? Any questions? Yes.
So we understand the difference between x and y.
Between this and this?
Yeah.
Yeah, this.
Why do you need both?
Sorry?
Why do you need both?
Why do you need both? Because we are working with vectors, right? Like I said here in the top, the vector here, you need to have these two, intensity and direction. You need to have these two informations, right? That's exactly what you have here. If you look carefully, here, this term here will give you what? Intensity. This term here will give you direction. All right? That's why you have two. When you multiply both, you have these two information. You have the intensity and the direction. Always like that, okay? So that's why you need here a unit. That's why you need I to be a unit vector. Because if it is not a unit vector, when you multiply I by AX, you will get a wrong intensity for AX, right? Right? If you multiply AX by 1, you will get AX, intensity AX, right? So, yeah. Okay. Now, what you can see here, you can see that we have AX plus AY. So if I add these two, I will have at the end my vector A. Correct? That is exactly, so I'm going to delete this. Let me just do this. So this is exactly what we are doing here. So I'm trying to reproduce here. So we have AX vector. So is this horizontal component here? This horizontal component. Can you see? And what I'm going to do is I'm going to include this vertical component AY. Right? I'm going to include it here, AY. Right? And what I'm saying here is that I'm adding AX plus AY, correct? That's what I'm doing here, right? So I'm going to do it here graphically. So in order to do it graphically, so I'm going to do the opposite, like I did in the opposite way, right? So I'm going to draw parallel lines here to this and to this, right? And then I just connect this point to this point, and this gives me my A vector. We call this the parallelogram rule, to add vectors graphically, right? Okay, so we saw here how to decompose a vector into its components along the coordinate axis, AX and AY. We saw then how can we obtain the vector by adding these two components, AX and AY. So this is a very common way of representing vectors. It includes all the information regarding intensity and direction of the vector. There is also an alternative way of representing this, which I tend to use more than this, which is I can say that my vector A is going to be represented by my X component, AX, and by my Y component, AY. Okay? We call this the matricial notation. All right? This is the... Oops. Yeah, we call this the matricial notation. All right? So this is very easy to understand. So the first component here is the component of the vector in the x direction, is this one. Okay? Sorry, I'm just trying to compose this. While this component here, the second one, this one is the component in the y direction, this one here. All right? Of course, if you have a vector in 3 dimensions, you will say, for example, if I have my vector A described in a 3-dimensional coordinate system, I will have a component in the x direction, ax, a component in the y direction, and a component in the z direction, right? Or if you want to represent it this way, I will have something like this. A equal to ax times I plus ay times j plus az times k, where k is also a unit vector along the z direction, okay? All right? So, let's do one example. Imagine, for example, I give you this vector. This vector A. Let's do a two-dimensional analysis, two-dimensional example. So this is my x-axis. This is my y-axis. All right? You can sit here. There's available seats here. You don't need to be standing there. Okay, so, and I'm going to say that this vector A makes a 30 degrees. So this angle here, from here to here, is 30 degrees. All right? I want to get the components of A all right? So what I will say is that we have to decompose this vector along the coordinate axis. So I'm going to decompose A in the horizontal x direction. So this vector here, I will call it AX. And then I can say that AX you tell me, how much is the norm or the intensity, or if you want, how much is this length of this vector? Yes?
AX cosine 30.
A norm of A cosine of 30 degrees. So I will say, norm of A gives me what? Norm of A gives me the length of my vector A, right? Gives me that length, or the intensity of vector A, right? So if I multiply this length, basically we have here a rectangular triangle, right? If I multiply that length, which is the hypotenuse, by cosine of 30, I will get, so what I'm saying is that if I do norm of A cosine of 30 degrees, like you said, this will give me what? This will give me is the norm of AX. The norm is always the intensity or the value or the length of the vector, right? So it gives me this length, right? Gives me this length here. Right? This length here is the norm of this vector AX in blue, which is basically the projection. So the norm of A cosine of 30 degrees is the projection of vector A in the horizontal axis, right? That's how you project a vector along a specific direction. So this is the norm, the scalar. I need now to multiply this by the unit vector, which is my unit vector I. So then I know that this norm of AX, or that length, is apply it over my x-axis. So I get the direction, right? And I need to do the same thing now for the y direction. I need now to project my vector A along the vertical direction. So what I'm going to do is I'm going to try to obtain this vector here, which I will say this vector is AY, right? I will try to obtain this vector. And then I can say that, so, and then I'm going to add, sorry, this is AX, you're correct. Then I'm going to say AY is going to be what? Is going to be again the norm of A times what? Now, sine, very good, sine of 30 degrees. And then this is going now to be along my y direction, which is defined by this unit vector j, right? And then now I can say that my vector A is going to be what? Is going to be the norm of A cosine of 30 degrees along the I direction plus the norm of A sine of 30 degrees along my J direction, right? Or if you want, I can use this space here. I can say that my vector A is going to be equal to the norm of A cosine of 30. Sorry. I think I don't have too much space here. Let me try to get some more. So what I was saying is that I can now say that my vector A in matricial notation is going to be equal to norm of A cosine of 30 degrees, norm of A sine of 30 degrees. Right? Okay? So it's very easy. For example, if I tell you that, imagine in this example, I tell you something like this. Norm of A is equal to, let's say, 10 kilonewtons. 10 kilonewtons. Imagine this vector A is a force. And then I tell you, okay, the intensity of this force, or the bar of this force, is 10 kilonewtons. Then you can define the force vector A by just replacing here the norm of A by 10 kilonewtons, right? The x component is going to be 10 cosine 30, the y component 10 sine 30, right? So, and if you look carefully, we are completely representing a vector by including its intensity and its direction and adding the components to get the final vector, right? So far, any questions? Can we continue? All right, so what am I going to do now is I'm going to continue with the same vector A. So I'm going to write it here. This is now a very important thing, what I'm going to do now. So we have this vector A, and what we have been doing so far is we have been describing this vector A in this XY coordinate system. Right? And then what I did was, I'm just going to do it again here. We obtained this AX component, and we obtained this AY component, right? That's what we did so far. Now, what I'm going to do is, or you might be asking, why did I choose this coordinate system, XY? Can I choose a different one to describe this vector? I can choose any coordinate system, right? For example, I can now say that okay, I don't want to use this coordinate system, but I want to use, for example, this one. Oops. Let me move this. Okay. All right, so I want to use maybe this one. So let's say this is x prime. This is y prime. It doesn't look like in the figure here, but x prime, of course, x prime is perpendicular to y prime, okay? They are orthogonal, they are perpendicular, of course, otherwise they will not be a coordinate system. They will not form a coordinate system, right? So, imagine, for example, I want now to describe my vector A in this new coordinate system, x prime, y prime. My question is, do you think the vector A that you have here in red, it will be different just because I'm describing it in a different coordinate system? Or it is going to be the same vector? Does it change? For example, if I'm saying this vector A, for example, is the velocity of a particle, okay? And this particle goes from, for example, this position A to this position B. Do you think that by changing the coordinate system that I'm using to represent the vector, do you think I am changing this velocity vector? Do you think I'm going from particle A to particle B, or I'm going to particle A to particle C, for example? Does it change?
No.
No, right? It's exactly the same vector, right? But something is changing here. What is going to change?
Yeah.
What? Yeah, the components. Very good. What is going to change is the components of this vector, because if I want now to describe this vector A in this new coordinate system, x prime, y prime, what I have to do is I have to draw parallel lines to this coordinate axis, right? And then this is going to be my component. I will call it x prime. And this one is going to be my component a y prime. Right? You see what happens? And then I can now describe this vector A in red in these two different coordinate systems. I can do something like this. Look at this. I can say my vector A will be, I'm going to use matricial notation. If I describe this vector A in the original xy coordinate system, I will get what? I will get ax, ay. Right? And if I describe this vector A in this x prime, y prime coordinate system, what I will get is, I will get the components ax prime and ay prime. Right? So, basically this tells us everything. The vector A in red here is the same. What is different is the components. Here in green color, you have the components in the xy coordinate system. In blue color, you have the components of the vector in the x prime, y prime coordinate system. Basically, the vector is the same, but by using different coordinate systems, basically what we are seeing the vectors from a different referential. Right? I can give you an example. For example, imagine something like this. Imagine this colleague here and this colleague there. Okay? They are both looking at me. I am the same person, right? I'm not a different person because he's looking at me and because he's looking at me, right? But he's seeing my right face and he's seeing my left face. But I'm the same person, right? I'm not changing. But they are seeing me from different angles. That's exactly what is happening here. By using different coordinate systems, we are seeing vector A from different referentials, different angles if you want. Only the components change, but vector A is exactly the same. Okay? So this is an important thing. So, you will start now to understand that we are going to work with vectors always.
And we need always to have a coordinate system to describe that vector. You are free to choose the coordinate system that you want. It's up to you. Many times we choose that for convenience because sometimes it's easier to represent a vector by choosing this coordinate system and not the other one, right? Okay? So, any questions? Everybody understood this? So this is the situation with vectors. We always have coordinate system that is very different from scalars, right? So if you are happy with this, I will then move to the next thing, which is dot product and cross product between vectors, okay? So let's start with the dot product. So imagine, for example, if I have vector A, if I have vector B, all right, if I have these two vectors, if I want to do the dot product between these two vectors, we represent like this, A dot B. Okay? That's why we call this dot product. And the result of this dot product is going to be a scalar, not a vector. Okay? This is very, very, very important. And that scalar is given by the norm or the intensity of vector A times the norm of vector B times cosine of the angle between these two vectors, this angle alpha. Okay? So as you can see, the result of this is a scalar, not a vector. Norm of A is a scalar, norm of B is a scalar, cosine of alpha is a scalar, so the result is a scalar. If, for example, there are other ways of doing this dot product. For example, if I say that my vector A is given by these components AX, AY, AZ. So I'm doing in 3D now. AX, AY, AZ. And for example, if I tell you that my vector B will have these components BX, BY, BZ. If I do the dot product A with B, I can do it in something like this. I can write this vector A. I can write the transpose of vector A, AX, AY, AZ. And then I do the dot product with vector B, BX, BY, BZ. All right? And basically, the result of this is going to be something like this. So I multiply, so I'm going to use colors now. I need to multiply the first component of my vector A with the first component of my vector B. And the result is going to be AX times BX plus. Then I go to the second component of A. I multiply with the second component of B. Oops. Then you get plus AY, BY, plus, and at last you do for the Z component. You multiply AZ with BZ, and then you just add it here, AZ, BZ, right? So two different ways of of calculating the dot product. They are summarized here. The first one is if you know the norm of these two vectors, A and B, and if you know the angle between the two vectors, you just multiply the norms with the cosine of the angle, right? And then you get the internal product, or the dot product. If you know the components of the vector in a coordinate system, AX, AY, AZ, BX, BY, BZ, you can do the dot product by multiplying the first component of each vector plus the second component of each vector plus the third component of each vector. This should be exactly the same at the end, right? So let's do an example of this. Let's do a very easy one. Let's say this angle alpha is 90 degrees. So I'm going to use here. So let's say I give you vector A. So vector A is this one, and vector B is this one. This is 90 degrees, they are perpendicular. I'm going to give some values here. So let's say norm of A, or the intensity of A is 10. I'm not going to put any units. Norm of B, 100. Okay? So basically we know we can define, now I'm going to define a coordinate system. For convenience, I'm going to say my x-axis is this one. My y-axis is this one. I can do that. I show you that I can use any coordinate system I want. And then if I do this way, it's very easy to represent or to obtain the components of these two vectors in this coordinate system. You might say vector A, the components are, so this is a 2D analysis. Vector A, the components are, so we have vector A is only has a component in the y direction, right? The component in the x direction is 0. And the component in the y direction is the norm of A, which is 10. This is my vector A. You all agree? My vector B, it only has a component in the x direction. And that component is, the norm of B is 100. So this will be 100, 0. Okay? Everybody's following? So if I do now the internal product using the first method, right, which is this one, norm of A is 10, norm of B is 100, cosine of 90 degrees is 0, the result is 0. Right? If I do the internal product A with B by using the components of the vectors, I will have what? I will have vector A transpose 0, 10. I will have vector B 100, 0. The result is going to be what? This times this, which is 0, plus 10 times 0, which is 0 as well. The result is also 0. Correct, right? And from this example, you can also see what is the meaning of the dot product. Dot product basically is the projection of one vector in the other's vector direction. As you can see in this example, I'm projecting vector A. When I do the dot product A with B, what I'm doing is I'm projecting vector A in B direction. And as you can see, they are perpendicular, right? So that projection should be 0. Right? So that is the meaning of internal product. What I suggest we do now is we do the cross product now, and then we do a break. What do you think? Okay. It's good. I always have a okay in this question. All right, so let's do cross product now. So cross product. So imagine I want to do the cross product of vector A with vector B. All right? The first important thing is the result of this cross product. So basically I'm going to say that the result is going to be a vector, not a scalar now. All right? So the cross product, the result is a vector. I call this vector vector C. And it's going to be obtained by doing a cross product of vector A. Cross product, we represent the product with this cross here, A with B. And the most important thing now is this property of the cross product, which is the resulting vector C is perpendicular. So I'm going to put it in red, sorry. So this vector C is the result of this cross product. And the result is going to be a vector. Is going to be a vector which is perpendicular to vector A and perpendicular to vector B. So I can say something like this. Vector C is perpendicular to vector A, and vector C is perpendicular to vector B. Right? You don't need to copy this because I'm going to make this available in Panopto, right? I think it's Panopto. I will upload this. So you will have Panopto or Blackboard, okay? Don't worry. I prefer you to pay attention, make questions if you are not understanding, all right? All right, so this is an extremely important property of the cross product. The result is a vector that is perpendicular to A and B. It's perpendicular to the two vectors that we are using for the cross product, right? And I'm going to show you that is the case. We are going to use the cross product, for example, to calculate the moment produced by a force, right? This is very convenient to be done in 3D analysis. For example, to calculate the moment produced by a force in 3D analysis, it can be very hard if you don't use the cross product. Because in order to obtain this cross product, so in order to obtain my vector C, what I'm going to do is, imagine I have vector A with these components, AX, AY, AZ. So this is my vector A, right? I can put it like this. This is my vector A. And I'm going to do the cross product of my vector A with my vector B, with components BX, BY, BZ. I'm going to do this cross product, okay? So this is going to be my vector B. And the way you do this is by doing a cross product of each component. So I'm going to explain it how we do that. So let's start with the x component of the vector, okay? So what we are going to obtain is, so this is going to be the result, my vector C. So let's work this first component here in the x direction. How do I obtain this component? I obtain this component by doing this cross product. AY times BZ minus AZ times BY. So I'm going to put some signals here. So we can. So this component here is going to be, look at this, AY times BZ minus AZ times BY. That's why they call this the cross product. We are doing a cross product. Right? This is for the X component. For the Y component, this one here now, the second component of this vector C. So I will try to erase this now. Let's see if it works. Okay, good. Now, for this second component, I need to do this cross product now. AZ times BX minus AX times BZ. There is a change in the signal here. But anyway, you will have here the final. So we are doing again the cross product. And AZ, let's do it blue. AZ times BX minus AX times BZ. This gives us the Y component of this vector C. Now the Z component. For the Z component, for this component here, all right, I'm going to do this cross product now, AX times BY minus AY times BX. So basically, if I want Z component, what I do is I ignore these Z lines and I do the cross product with the other two components of the vectors. If I want the X component, I ignore this and I do this cross product. Right? You see how it works? If I want the Y component, I ignore this and I do this cross product. It works like that. Right? So this component here, for the Z component, what I'm going to do is I'm going to do this cross product here. And then that will be AX times BY minus AY times BX. This will give you the Z component. Another good way to check is, if you look here carefully, we have AX, AZ, and Y. So if you have here, for example, AX, AY, something is wrong in your cross product, okay? Same thing for the B here. We have BY, BX, BZ. They need to be all three different, right? All three different here, you see? So this gives you the cross product. I'm going to show you, just before the break, a quick example. Again, now we have to do in 3D. So let's say I'm going to write here so let's see, X, Y, Z. So X, Y, Z, 3D coordinate system. I'm going to define here two vectors, A and B, in blue. For convenience, I'm going to say my vector A is aligned with X. So this is my vector A. My vector B is aligned with Y direction. Okay? And I'm going to do the cross product of A cross product with B. The result, you know, the result needs to be a vector which is perpendicular to A and B. In this case, needs to be a vector that is coincident with Z direction, right? Look, A is X direction, B is Y direction. So a vector that is perpendicular to X and Y direction needs to be a vector in Z direction. Agree with me? So let's see if that is the case. How can I write vector A? So let's say vector A, for example, it only has component in the x direction. Let's say 10, 0, 0. Agree with me? This is a vector with only component in the x direction. Vector B only has component in the y direction. Let's say 10 as well in the y direction. So this is my vector B. So let's do the external product of A, 10, 0, 0. External product with B, 0, 10, 0. So let's do the cross products now. Let's start with my the x first. So I need to do this cross product now. This times this, which is 0, minus this times this, which is also 0. Agree with me? So the first term in the cross product is 0. Let's go to the y component now. For the y component, what I do is I ignore the y, and then I do this cross product here. This times this, which is 0, minus this times this, which is also 0. Agree with me? So the y component also 0. Now, z component, sorry, I ignore the z line here and I do this cross product. This times this, which is 100, minus this times this, 0. So the result is going to be 100. And this in fact is a vector along this z direction, and vector C, for example, and the norm of C is 100. The norm or intensity of this vector is 100 and is aligned with z direction, right? Okay? So as you can see, the result of a cross product is a vector perpendicular to the two vectors used for the cross product. The result of a dot or internal product is a scalar. Very important. All right? No questions? So let's do a 5 minutes break. 7 maximum, sorry. Maximum 7. There was a very interesting question during the break regarding the cross product that I would like to address to all of you, which is, the question was during the break, the norm. So basically, the norm of the result of the cross product, the norm of this vector C, what does it represent? And what it represents basically is this. It represents the area. So we had vector A and vector B. This area here is basically the norm, or the norm of the result of the cross product. Right? And we can easily check in this example. Look at this. How much was this length here? This length is what? Is the norm of vector A, which is 10. By the way, how do you calculate the norm? The norm of a vector, vector A, for example, is the square root of x component square plus y component square plus z component square. In our case of our vector A, we have vector A, ax is 10, then everything else is 0. So we have square root of 10 square, which is equal to 10. This is the norm of our vector A, which is exactly the same as our vector B. The norm of B is also 10. So if this is 10, the length of my vector B, or the norm of vector B, is also 10. So this area is going to be 100. 10 times 10, which is the norm of vector C, the result of the cross product. Okay? So cross product has a lot of information. First, give us a vector that is perpendicular to A and B, and the norm of that vector is the area formed by the parallelogram between A and B. All right? Okay? I hope it answered your question. I don't know what it was, but... Okay, so let's move now